So in the last two lectures we talked about electron configuration and how the periodic table tells us the electron configuration. And we can look at the electron configuration of an ion or an element and use this Aufbau principle to build up a electron configuration. So for something like oxygen ion, we can look at the periodic table. From the location of the periodic table, we can look at the oxygen and say that these are p electrons and there's 4 p electrons in this subshell. So for the oxygen atom, it would be 2p4, but we've gained an electron. So rather than being in the 2p4 subshell, we know that this is actually gaining electron to be 2p5, and so the electron configuration would be 1s2, 2s2, 2p5 for the O- ion. We can do a similar analysis for zinc. Zinc is a transition metal, so we know that it has electrons in the d orbitals, and it's got 10 d electrons, and so we know that there are 10 d electrons, and again we can build up based upon our location on the periodic table. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, done. And that would be the electron configuration for zinc. Again, magic chemistry tool comes into play. 1s, 2 electrons, 2s, 2 electrons, 2p, 6 electrons, 3s, 3p, 4s, and then comes the break, 3d, back to 4p, and then again 5s, 4d, then back to 5p, and then 6s, and then of course there's this break here, the lanthanides, which jump down to the F block, and then those start at 4f, and then go back to, this would be, I guess, 5d, and then back to 6s. So it gets a little confusing down here. All right. But you can use the periodic table again as your guide. Besides electron configuration, we also talked about orbital configuration diagrams, which relies on the same information. So if we look at O negative, we know that it is 1s2, 2s2, 2p5, and we can draw an orbital diagram for the valence shell, just the s and p electrons, and we know that 2s and 2p, drawing out the orbitals, hence the name orbital diagram, and we can then fill those orbitals with electrons. 1s, 2, 2p, 1, 2, 3, 4, 5. And so, again, notice, fill the orbital completely. This is called Hund's rule. We don't pair them up unless we have to. And then we put the last 2 electrons in, pairing them, leaving 1 unpaired electron, which we could then say that this is a paramagnetic compound having unpaired electrons, whereas diamagnetic compounds have all of their electrons paired. So that is the how. Okay, this is how the electrons are arranged. And now let's talk about why. Remember the jump rope example, the standing wave that we had? All right. So it turns out that every particle has wave-like properties associated with it. What that means is if you take a particle and you place it in a small enough region of space, its wave-like properties start to become obvious. This has to do with, in part, with the Heisenberg uncertainty principle. You can know its position or its momentum, but you can't know both of them with absolute assurance. So if you make a box small enough, you start to get some gray areas associated with this. Another way of conceptualizing it is this standing wave. If you have a box, this wave bouncing back and forth, only certain values will give you a stable wave structure. And as we were demonstrated in class, as you increase the energy, you get more and more of these, what we call nodes. Nodes would represent areas where the phase changes. So here we have the jump rope and its amplitude in one location, its amplitude in the other. And the phase of these two components is opposite. One goes up, one goes down. Right? So this is, again, a standing wave in a box, or a particle in a box. And the only way we can generate stable wave structures in that box is by increasing the energy of each of those waves. And as you increase the energy, you get more and more of these nodes and more of these lobes. So, someone came along named Schrodinger, and he realized that this wave, there's a function associated with it, a mathematical function that can be used to describe its properties. And so what he was able to do was to develop a function associated with waves in 3 dimensions. So what we have actually here is a one-dimensional wave. We only really care about it in the energy that's associated. There's 2-dimensional waves and 3-dimensional waves, and so he decided to solve these equations for 3-dimensional waves. And he developed something called the Schrodinger equation. And so what he was able to do was to develop a 3-dimensional wave equation, an equation that describes the waves in 3 dimensions, that relates the energy to the nature of the particle. And what he found is that these energies corresponded really well to the energies seen in the hydrogen atom. And what he found is that the L energy could be predicted as a function of 4 different numbers. And so he could plop in 4 different numbers, which we now call the quantum numbers. And using these 4 numbers, he could uniquely describe the energy of each electron in the atom. This wave equation, often given the sum psi, when you solve it, it turns out to be a function of a number of different variables. And these variables, we've actually seen some of them before, and they each have a consequence. So the wave equation relates to the energy, but there's a more useful bit of information that comes out of it. And it turns, for us, what we really care about is not the wave function itself, but usually the probability associated with finding the electron. The short answer is the wave function the probability function of the wave function tells us where our best chance of finding the electron is. So there are 4 quantum numbers associated with these wave functions. And those quantum numbers are each uniquely named. The gist of it is that every electron in an atom will have a different set of quantum numbers. So every electron in a given atom has a different set of quantum numbers. Those quantum numbers are like an address that uniquely identifies where we'll find that electron. So those quantum numbers are given the symbols M, L, M sub L, and my favorite, M sub S. These are the 4 quantum numbers. And they're just numbers, but they have a specific set of rules associated with them. They only work to generate a valid solution for the wave function under certain conditions. Right? We've already seen n. Right? N is the principal quantum number. The principal quantum number still is exactly the same as what we've been talking about it before. It is the primary energy level. It's the average energy of the electron. It's related to that. Things that are in the first shell versus things that are in the second shell. Things that are in the second shell, on average, have a higher energy than things in the first shell. The end. That's what n tells us. Principal quantum number. We've already seen that n can only have values equal to 1, 2, basically some integer. Right? We've only seen up to about 6 or 7, but all of the elements on the periodic table can be described with 6, except maybe some of the radioactive ones. No periodic table. I was wrong. N is equal to 7. Francium. So you can actually describe some of the later elements with. But there's another hidden aspect of it. The principal quantum number is also roughly the distance away from the nucleus. N is equal to 6 electrons are on average further away than N is equal to 3 electrons. I mean, there are some, some deviations. We've seen this, where the 3D are a little higher in energy, which sort of suggests they're a little further away than the 4s. So, again, in general, this represents distance away from the nucleus. Now, the values of L is the angular momentum quantum number. And we've already seen this indirectly, what L relates to. Angular momentum quantum number relates to the subshell. So this is roughly the shell. This is roughly the subshell. Additionally, one of the hidden things that's in there is the type of subshell. The angular momentum quantum number influences the shape of the subshell. It turns out that these subshells are not these little spheres that nest around the atom like orbits. The subshells have distinct shapes that actually influence a large number of their properties. L can only have values from 0 up to n minus 1. So what does that mean? If, for instance, in the third shell, n is equal to 3, L could have any of the following valid values: 0, 1, or 2. Additionally, this also tells us the number of subshells. In the third energy level, there can be 1, 2, or 3 subshells. But numerically, we start at 0 in those cases. The L is equal to 0, L is equal to 1, or L is equal to 2 subshell. Again, these are unique identifiers for L. An electron is only going to have one L value, one N value, one M sub L, one sub S. Right? So even though there are multiple values that are possible for L, only one of them applies to a given electron. And again, this relates to the shape of the electron region that the electron resides in. This is the location where you can find the electron, the shape of the orbital associated with it. Now, the other quantum number, M sub L. M sub L is what we call the magnetic quantum number, and it relates to the orientation of the region within the subshell. For the most part, orientation doesn't matter, except in the presence of a magnetic field or some sort of spatial geometry influencing substance. Where it really shows up actually is in molecules, when atoms start to bind to one another. But another way of thinking about this has to do with orientation. This is sort of orientation of the subshell. Or another way of thinking about it is orientation of the orbital. We've already laid these things out already. The shell represents the principal quantum number, how far away you are. Within that is subshells that have different energies, and within those there are orbitals. So what we're just doing is we're actually codifying these relationships using a series of numbers. It turns out M sub L can have values, numerical values, that are from minus L to 0 up to plus L. So if L was equal to 5, that would mean M sub L would be equal to minus 5, could be equal to minus 5, minus 4, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, plus 4, plus 5. all of which would be valid values for m sub l. Again, an electron only has one m sub l number. L is equal to 2. What we see is that m sub l would be equal to negative 2, negative 1, 0, plus 1, or plus 2. What these represent, notice, if you have a d orbital, 1, 2, 3, 4, 5, these would represent the 5 different orbitals into which you could place those electrons. So again, mega quantum number is the orbitals, the actual orbital within the subshell, within the actual location. And lastly, m sub s, which represents the spin quantum number. It has the value of plus 1/2 or minus 1/2. It can only have those values. That's why it's my favorite. It's the simplest one. All right. So what this relates to is when you pair up an electron in an orbital, all of the other quantum numbers are the same. They're in the same shell, they're in the same subshell, they're in the same orbital. And so for them to have a unique identifier to describe them, you also have to take into account the spin, which relates to the phase of these particular electrons. And so they reside opposite of one another within the atomic structure of the atom. So these two electrons would have the same set of quantum numbers, n, l, m sub l, but their m sub s values would be different. And we would describe their quantum numbers. Traditionally, we put the quantum numbers that describe an individual electron in a bracket to show it, because they show up as a function, sort of as a function of this sort of wave function. But we can ignore that last little bit of fun. So these quantum numbers are a unique address for each electron present.